Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and this is the second continuation of the lecture entitled Fundamental Theorem of Calculus, FTC 1. Okay, when last I left you, we had this piecewise function, and you were supposed to evaluate these two integrals, the definite integral from 10 to 22 f of x dx, and b was the definite integral from minus 2 to 3 f of x dx, where f of x was defined this way. Now you might have finished this problem already, but in case you didn't, you know what to do. Let's see how you did. Well, here's the graph of the function, and you see the function actually changes definition. It is discontinuous at 1 because the limit from the left side is about 3 and the limit from the right side is 6. So you see it is discontinuous. That means you can't integrate the whole thing, at least if you go across this point of discontinuity. Now the first integral, though, that you had started at 10 and went to 22. So you see we're way out here, and that interval of integration does not include the point 1. So that means you're really integrating the constant function 6 over that entire interval. Now this is one of the things that I said before, and here I use the fundamental theorem of calculus to do this. So the 6 just sits there. That's an x to the 0, so it's going to be x over 1. That's 6x. I evaluated those 2 points. I plug in 22, subtract, plugging in 10, and I get 72. But also, if you have a constant function, a flat function over an interval, it is going to be the constant times the length of the interval. So you see, I would have done this in my head and said that this is going to be 6 times 12, or 72. But the other point is a little bit more difficult because we're going from minus 2 up to 3, and that goes across the point of discontinuity. So what we have to do is we have to split this integral in two. So the integral from minus 2 to 3 f of x dx is the integral from minus 2 to 1 f of x dx, and that gives us this area. And then we go from 1 to 3 with f of x, but now it's beyond the continuity and it's changed its definition. So you see down here, the first integral, we're going to be using the value 3x squared, and for the second interval, we're using the value 6. So I use the fundamental theorem of calculus both times, and I do the calculations, and I get 21. So you see we had to break that into 2 pieces. Okay, here's another integral I'm asking you to evaluate. Evaluate this integral. This is the integral from 0 to 3, the absolute value of 3t minus 5 dt. You know what to do. Let's see how you did. Well, what happens is, and you know that the absolute value of something is x if x is bigger than or equal to 0, and it's minus x if x is less than 0. So you see, if I'm somewhere between 0 and 5 over 3, then this is negative, so it's going to be minus 3t minus 5. So we're down here because 3t minus 5 is negative. But from 5 over 3 to 3, it's positive, and so it's just 3t minus 5. So I integrate the two of these. Now, so this, I distribute the minus sign, getting this, and this is just fine the way it is. So I go through and I integrate term by term here. I get this. I evaluate it at the endpoints, and here I do it term by term. You should understand where all these numbers are coming from. I evaluate it at the endpoints using the fundamental theorem of calculus. So the first one, I'm going to plug in 5 over 3. And I'm going to subtract this minus sign I'm showing you is the minus sign from the fundamental theorem of calculus. I plug in 0 and I have 0. So that completes the calculation for this one. I go to this one, I plug in 3, and I get this. But then I'm going to be subtracting. This is the minus sign from the fundamental theorem of calculus, and now I'm plugging in 5 over 3 into there, and I have to do all of this calculation, and I have to be careful with my signs. But you should have gotten 41 over 6. Next, recall that an even function, you studied this in your algebra, is any function which satisfies f of minus x equals f of x. That means you're symmetric with respect to the y-axis. And examples of this are y equals x squared, but we also learned from our trig that y equals f of x equal cosine x is also even. An odd function is any function which satisfies f of minus x is equal to minus f of x. And examples of odd functions are y equals f of x equal x cubed and y equals sine of x. Now, there are some nice facts that help you when you're integrating even and odd functions over an interval going from minus a to positive a. So if a is an even function, then the integral from minus a to a f of x dx is twice the value of the integral from 0 to a of f of x dx. This is useful because often 0 is an easy number to plug in where minus a might not be. Likewise, if f is an odd function, then the integral from minus a to a of f of x dx equals 0. So you see, in order to use these facts, the limit of integration must be the same number, but with opposite signs. Let me show you a picture of this. So you see, this is the sine function, and if I'm integrating from minus pi to pi, what happens is this area is positive and this area is negative, but you can see they cancel each other out. That's the odd function. If I'm going from minus pi to pi with with the cosine function, you see this area here, the total area is twice this area, and so it makes an easier calculation. So here's an example I would like for you to do. So you integrate each of the following. We have two problems, A and B. You know what to do. Let's see how you did. Well, the first one is even because x to the fourth is even, x squared is even, and 1 is an even function. So that means the integral from minus 2 to 2 is twice the integral from 0 to 2. So the 2 just sits there, but look how easy it is to plug 0 into this after you integrate it. So we're really just plugging 2 in. Now you should really do this calculation because on a test I would want you to do it, but the answer is 748 over 15. So you see that cut our calculation time in half, at least. Now here is part B, and x to the 5 is an odd function. Sine of x is an odd function, so the whole thing is an odd function, and we're going from minus 10 to 10, so we know immediately that is 0. Now you should note that the limits of integration are important here, and if we take this last integral, this one, as an example, if we just did a small change going from minus 10 to 9, not to 10, we would plug in these things and we would get something that's almost 80,000, negative 80,000 as an answer, a long way from 0. So a small change can make a big difference. We will continue this in 36.3.